Hi, Lester, Wisher Engineer. In one of my latest videos entitled Crescent, Futuristic Thrust and Cut Kukri with Tactical Armored Sheath Bracer Tested, I introduced a new and experimental scientific method for testing weapon cutting performance called the impulse cut method. I encourage you to check that video out to see the videos of the testing that we performed, because I'm not going to show all of it in this video. In that video, I said that I would put out a dedicated video going into a little bit more detail behind the impulse cut method. And in this video, I'm going to attempt to do that. As some additional background to the impulse cut method, before we go on, I put out a YouTube poll about a year ago, and the respondents made it quite clear that they wanted me to develop a more scientific, objective, and systematic way of measuring weapon cutting effectiveness. Hence my work on the impulse cut method. So don't complain to me about my audacity at trying to make weapon cutting tests more scientific. Take up your complaints with the 83% of respondents who voted for me to do this thing. There's a long history of human beings using various methods to test weapon cutting effectiveness. As an example of one of these historic practices, there is the art of tamashigiri. Excuse my pronunciation. I'm not going to speak on this topic in any great detail because I'm not an expert in any of the Japanese arts. I'll have an excerpt on the screen from the Wikipedia article, which you can look up at your leisure. Follow the links there as you wish. Suffice to say at this point that cutting through specially prepared rolled up tatami mats is still practiced extensively to this day. As can be seen from the Wikipedia article, during the Edo period, an attempt was made to make the cutting tests as objective as possible by only choosing the most skilled swordsman to test the swords, so that the swordsman's skill was not questionable in terms of determining how well the sword cut. While this is a reasonable attempt at objectivity, it still introduces significant limitations and drawbacks. But before I go on, folks on the internet tend to get emotional about things for no reason whatsoever. So let me make something quite clear before I start discussing the limitations of test cutting. My criticisms are in no way a direct criticism of the art of tamashigiri or any of the other test cutting performances for that matter. In no way am I implying that cutting tests do not require significant skill, nor am I implying that they are completely irrelevant. My criticisms are directed purely at the compromised scientific value of cutting tests. So back to the scientific limitations of traditional cutting tests. Firstly, even though the most skilled swordsmen were chosen, how can there be any guarantee that their skill was evenly matched, was consistent, or even high to begin with? It could only have been down to a mix of objectivity and subjective assessment of the swordsman's skill. When the basis of your objectivity is a subjective assessment of someone's skill, you're already on pretty shaky ground. There are a lot of showmen and con artists out there who manage to convince many that they are indeed Captain Amazing, when they are, in fact,
Sergeant Major.
Combined with normal human performance variation, the subjectivity leaves conclusions derived from these tests quite open to criticism. Secondly, the data derived from these tests would be limited in a number of ways. The tatami mat targets could be inconsistent, leading to inconsistent results. The granularity and low resolution of the data derived from the tests doesn't allow for a comprehensive and higher res comparison between different weapons. This leads to very subjective data analysis, such as sword A cuts through 2.5 tatami mats, and sword B cuts through the same number of tatami mats, but it felt easier. Hence, sword B is better than sword A. As you can imagine, this doesn't allow for very fine comparisons between weapons, or for small weapon design changes to be analyzed effectively. Finally, Scientific advances have brought us into an age when we really need to be able to provide a suite of more scientific parameters for weapon performance than cuts through 6 tatami mats in one swing with relative ease. For all of these reasons, and because 83% of you asked us to do this, we have developed the impulse cut method. However, before we go on to discuss the impulse cut method, we should first understand what cutting is. We all know instinctively what the act of cutting is, but for a greater understanding of how the impulse cut method works, I'm going to state the obvious. Now, as you can hopefully see in my poorly edited Windows Paint image, when a blade cuts into a material sample, it does three things. It severs intermolecular bonds between constituent particles in the material sample, which requires energy. It has to push the constituent particles out of the way on either side to make way for the blade to continue on its magnificent journey through the material sample. This also requires energy. It also transfers a certain amount of impact energy into the material sample through the resistance of the intermolecular bonds between constituent particles to the act of braking, and through friction with the constituent particles as it moves through the material. Well, now that I've stated the obvious, I can go on to discuss the impulse cut method. Briefly, the impulse cut method is based on our impulse block method for measuring human striking characteristics. The impulse block method allows for a very comprehensive analysis of human striking and has been independently tested for validity and reliability as part of a study by the University of Southern Queensland. In addition, it's forming the basis of at least one other study which is running currently. In a nutshell, the impulse block equipment consists of a specially designed foam spring called the impulse block attached to the front face of a load cell that records force input. Using the measured values from the load cell, it becomes possible to calculate a number of characteristics associated with the impacting object. The primary characteristic of interest in this case is impulse, or change in momentum imparted by the strike. For a more detailed explanation of the impulse block equipment and methodology, you can see my other videos on the topic. So what we did was to use the impulse block method as a basis or foundation for measuring cutting efficiency. The impulse values were of most interest to us because the basic equation for impulse from Newton's second law can potentially be combined with the equation for work done or energy transferred to indicate the amount of energy imparted. The basic idea was to perform a cut against a sample made of a particular material fixed to the front of the impulse block, and then measure the depth of the cut and extrapolate the energy inherent in the cut based on the cut depth and the recorded impulse. Simple enough? Well, not quite, because the energy calculated based on the cut depth and the recorded impulse does not actually reflect the energy required to cut the material sample. As you will remember from our discussion of what cutting is, the energy used to sever intermolecular bonds and displace the test cutting material to either side to allow the blade to pass through cannot actually be measured using the type of setup that we have developed. The load cell behind the impulse block will not detect energy used to sever intermolecular bonds, because a load cell can't do that directly. Nor will it detect the force used to shove the material to each side of the blade, because those forces are actually applied essentially at right angles to the direction in which the load cell measures force, which is typically into the load cell or away from it. The energy converted in cutting through the material causes obvious permanent deformation and mechanical damage to the cutting medium sample, and is thus converted in causing that damage, so it cannot be measured using the equipment we have access to. However, we can still combine Newton's second law with the equation for work done to calculate the impact energy associated with the cut depth. This yields a value in joules, but it's not the energy converted in cutting the material. Rather, it is this spillover impact energy associated with the cut, communicated into the test cutting sample through its resistance to being cut. So essentially it's being pushed into the load cell. This value in turn can be further processed by dividing it by the cut depth to get a value in joules per meter, which reflects the spillover energy per unit meter associated with the cut. So of what use is that value? Well, it's actually quite valuable because while not being a direct measure of the energy converted in a cut, it does reflect the cutting efficiency of the weapon. It scales inversely with the depth of the cut and directly with the impulse. The higher the energy per unit meter associated with the cut, the lower the cutting efficiency of the weapon, and vice versa. So if a weapon impact yields a very high impulse but only causes a very shallow cut, the energy associated with that cut will be relatively high per unit meter. This would be indicative of a weapon that is quite inefficient at cutting because it takes a lot of energy to perform a relatively shallow cut. Imagine a dull blade that you have to hammer into the target at great effort to achieve any level of cut depth. Whereas if a weapon impact yields a low impulse but cuts deeply, the energy associated with that cut will be relatively low per unit meter. This would be indicative of a weapon that is quite efficient at cutting because it takes far less energy to perform a relatively deep cut. Imagine a very keen blade that slips smoothly through the target medium, costing very little effort on your part to cut deeply. I'll also use another two hypothetical examples to illustrate how the system works. If the chosen test cutting sample was a hypothetical block of air, for instance, the blade would just pass through the air, cutting it cleanly, without the block of air posing enough resistance to the blade for any measurable impulse to be transferred to the impulse block and load cell. So that block of air won't be pushed into the load cell, at least not enough for the load cell to measure anything. So because the blade was very effective at cutting the air, some of the energy in that blade swing was converted into cutting the air, while the rest remained as kinetic energy that would have had to be reabsorbed back into the wielder's body in some way. Of course, depending on the size of the block of air, there will probably be quite a bit of energy remaining in the weapon swing. Most of the remaining energy of the swing that's not converted into cutting the air would have to be absorbed, as I said, back into the cutter's body to avoid impacting with the load cell. On the other hand, if the chosen test cutting sample was a hypothetical block of hardened steel, the blade would just strike the block without cutting it at all, transferring all of its impact energy into the impulse block and load cell and converting none of its energy into cutting at all. So hopefully those two hypothetical examples carry home a little bit more about how the system works. The beauty of using the impulse cut method is that it can yield a numerical value that can be compared between weapons, allowing very fine comparisons and analyses to be performed on weapon cutting efficiency, obviously within the limitations of the error associated with the equipment. In addition to that, it removes some of the subjective elements of the unconscious bias that may be present in the person performing the cuts. Perhaps the cutter swings with more energy with one weapon than another. In that case, if we were just measuring cut depth, the results would be very subject to how hard the cutter was swinging one weapon over another, with no way of knowing, aside from how the cutter felt, how that was affecting the comparison. This could be due to subconscious bias, as mentioned, or simply as a result of basic human performance variation. Due to the fact that we are correlating impact energy and cut depth to find cutting efficiency, a great deal of human performance variation is actually removed from the analysis. A higher energy swing with a weapon will not necessarily yield a better cutting efficiency score over a lower energy swing with the same weapon. The cutting efficiency score should be relatively consistent for a particular weapon, given a particular strike and a particular striking point along that weapon blade, regardless of how hard or soft you swing it. Within certain practical limits, of course. We still need to perform many more tests to confirm this. So in order to realize the impulse cut method practically, we had to adapt our impulse block method to measure impulse associated with cutting through a sample of a particular medium or material. The nature of the cutting sample itself was a technical challenge that had me thinking and rethinking things for some time. In fact, this was possibly the single biggest technical hurdle, and the reason that it took me so long to come up with a practical system. The cutting samples had to be relatively consistent between individual samples, not particularly damaging to blades, allow for relatively clean cuts to be made, in other words, no grain or inconsistency in the material that would cause the blade to cut differently in different regions of the sample, and ideally should be sufficiently robust enough to totally absorb the energy of the blade, of the cut I should say, without the blade traveling through the whole depth of the sample and impacting the shield plate mounted on the front of the impulse block. I considered all kinds of different samples, such as blocks of paper sheets, blocks of ballistic gelatin, blocks of ballistic clay, amongst many other things. I even considered using a big block of silly putty, but that was just a silly idea. I finally decided that a type of card would be best because it would simplify the measurement of the cut depth. This kind of excluded blocks of material, like ballistic gelatin and clay, because measuring cut depth in a block, a sample block, would be a lot more complicated. Think of a curved blade causing a single cut of varying depth in the block. You'd have to perform some kind of cumulative average, and you'd have to hope that you actually got that depth right, that the sample didn't close back on itself. Just a lot of technical hurdles to using that approach. I was also unsure of whether or not I could get a practically sized sample of these materials that would fully absorb the energy of the cut before the blade penetrated to the back plate of the impulse block. Wooden cards would not do because of the inconsistency introduced by the wood grain, and due to the fact that wood can be brittle and shatter under impact instead of just being cut. Finally, after much cogitation and angst, I decided on using MDF, or medium density fiberboard, as the medium to make the cards out of. I also built a card mounting structure that affixed to the front of our impulse block that looked a bit like this. Being an engineered product composed of individual wood fibers bound in resin, the consistency of MDF is high. It's relatively non-damaging to blades and is substantial enough to fully absorb the energy from a cut without the weapon passing clean through the sample or shattering and breaking. MDF board is also pretty cheap and freely available internationally, and can thus be used as a consistent cutting medium in impulse cut tests performed all around the world. In this case, I chose to use 9mm thick MDF board for the test cards because I had some lying around in my workshop. After a bit of experimentation whacking 9mm thick MDF boards with swords and kukris, I found the optimal width for the test cards. The cards would be fixed to the front face of the impulse block, and a cut would be performed into the edge of the MDF card. The cut depth would then be measured and used in the calculations. Impulse and impact duration would be calculated using the force time data from the load cell. Once we had the impulse, impact duration, and cut depth associated with a particular weapon, we could take these values and calculate the energy associated with the cut, as well as the energy per linear meter associated with a cut. These values could then be compared between weapons to ascertain which weapon cut with the least amount of effort or energy committed to the cut. Now, it must be said that one of the limitations of this testing methodology is actually the type of medium that the cuts are performed in this case 9mm thick MDF boards. This medium has its own characteristics, which may favor some weapons over others. So it should be noted that all measured and calculated values associated with these tests are specific to the type of medium used in the tests. Using a different medium, such as ballistic gelatin for example, would more than likely yield different results. There are also measurement errors associated with all pieces of measuring equipment and measuring methods, and the impulse block and impulse cut methods are no exception. Our equipment has been calibrated and repeated drop tests have been performed to ascertain the percentage error associated with the impulse block method as part of the studies that we are undertaking in collaboration with the University of Southern Queensland. Based on these drop tests, our impulse block method is accurate to over 90% of the expected value. In other words, the error associated with the method is less than 10%. In addition, there is the potential for error in the measurement of the cut depth, although it would be pretty small because care is taken and measurements are performed several times over. I'm not going to repeat all of the test footage, the data analysis, and the discussion from my previous video. I'll play some of the testing now, just for a little bit of context, but if you're interested, I encourage you again to check that video out for yourself. Okay, so test 1, the cold steel kukri machete. Just say when.
Okay, when you're ready.
Right, so next is the titanium kukri called Preamble. Just say when.
Okay.
Next is the Tadaaa blades military surapati. So when. And last but not least is Crescent, and we'll see. Okay, so when. The results from that series of tests were quite interesting and a little bit counterintuitive. And it's actually, I found that the results were actually quite surprising. And that's actually what excited me, because my assumptions were challenged by the results. Sometimes that means that the tests were faulty in some way, and that can't be ignored. It's possibly the case due to the small number of tests performed. So more testing is required for confirmation. However, we did exercise a great deal of care in our testing and analysis, so I believe that the results may actually be quite valid. And that's really exciting, because when scientific investigation yields something that's not immediately obvious or that challenges pre-existing opinions, it could mean that there is scope for further development and understanding. In this case, the impulse cut method could form the basis of a series of studies that increase our understanding of cutting weapon design. It can also form the basis of a far more scientifically valid method of testing or comparing weapon cutting performance. Well, thanks for your time. I hope you enjoyed this video, and I'll see you all again next time. Cheers.